Welcome to the Explainer. Today we're tearing down the Light Dependent Resistor, or LDR for short. We are going to take some pretty complex solid-state physics and transform it straight into practical, actionable engineering knowledge you can use in your next hardware design.
So, ever wonder how a streetlight knows exactly when to turn on? It's not relying on a complex network connection or a fancy internal clock. It solves the fundamental problem of ambient light detection using a very specific, highly reliable hardware solution, the LDR.
Here's our roadmap for the Explainer. We'll be hitting physics and construction, datasheet decoding, circuit integration, real-world products, common failures, and finally, industry selection. Let's jump in.
Part 1, Physics and Construction. The quantum leap of photoconductivity.
Let's zoom way in to the atomic level to understand the actual engine powering this device. The magic here is photoconductivity. In pure darkness, an LDR is basically a brick. It acts as a total insulator because its electrons are locked up tight in the valence band. But the second light hits it, boom! It literally transforms into a conductor. Incoming photons excite those electrons, giving them the kick they need to jump the gap and become free charge carriers.
And the famous Planck-Einstein equation perfectly captures that exact energy threshold. A photon absolutely must have enough energy, which ultimately comes down to its wavelength, to force an electron across the semiconductor's specific band gap. If the photon's energy is too low, nothing happens at all. That is exactly why we use different LDR materials to target very specific wavelengths of light.
When it comes to manufacturing the physical package, the whole goal is maximum photon absorption. Manufacturers start with an insulating ceramic base, and then they lay down a polycrystalline material, usually cadmium sulfide, in this highly recognizable zigzag pattern. Why a zigzag? Well, it drastically maximizes the exposed surface area without making the actual chip massive. Then, the whole shebang gets sealed in clear resin or glass to let the light in while keeping moisture and contaminants out.
Moving on to Part 2, Decoding the LDR datasheet. Let's translate that physics into math.
Okay, here's the crucial math you're going to rely on. The resistance of an LDR drops non-linearly with light, governed by the power law equation. R is your resistance, E is the illuminance measured in lux, and gamma represents your specific material's sensitivity factor. Because it's a nonlinear relationship, if you plot it on a log-log scale, you get a beautifully straight line. That's exactly how engineers calibrate these things for accurate light meters.
If we pull up a standard, highly popular GL5528 series datasheet, the specs are pretty wild. Just look at the massive swing in resistance. At just 10 lux, which is fairly dim room lighting, the resistance is already down to between 8 and 20 kiloohms. But check out that response time, 20 to 30 milliseconds. In the modern digital electronics world, that is glacially slow. You really got to keep that latency in mind.
And get this, if you take a specialized, high-purity intrinsic device and stick it in absolute pitch-black darkness, the dark resistance can shoot up to a staggering 1 trillion ohms. At that point, it is effectively a perfect insulator.
Part 3, Circuit Design and Integration, Making the LDR Talk.
So microcontrollers don't care about resistance. They want voltage. How do we get there? The trusty voltage divider. By putting the LDR in series with a fixed resistor, you convert that crazy, wildly changing resistance into a nice, smoothly varying analog voltage. You just grab the signal right from the junction between the two components and feed it directly into your analog to digital converter. It's totally foolproof, needs zero active amplification, and literally costs pennies to throw on a PCB.
All right, Part 4, Inside real-world products, from phones to fighter jets.
So where are these components actually living out in the wild? Well, we all know they run standard automatic streetlights using cadmium sulfide for visible light. But here's where it gets crazy. Extrinsic, heavily doped LDRs made of lead sulfide or indium antimonide can actually see infrared. That means they're actively used in extreme applications, everything from thermal astronomy down to the mid-infrared guidance systems on actual fighter jets and missiles.
Part 5, Failures and Common Mistakes. Let's talk limitations.
Look, LDRs are incredibly versatile, but junior engineers trip up here all the time because they don't grasp the physical limits. First mistake, trying to use them for high-speed detection. With their high latency, they will fail miserably. Then you've got the memory effect, or hysteresis, which is caused by charge trapping in the bandgap. Basically, the sensor remembers if it was just in bright light, which totally skews your current reading. On top of that, temperature drift is severe, and moisture will absolutely destroy film-type LDRs. That means strict PCB layout rules, like applying conformal coating, are mandatory for outdoor use. Oh, and because cadmium is highly toxic, you're going to face strict RoHS regulatory bans in consumer tech today.
Finally, Part 6, Senior Industry Selection, choosing the right sensor for the job. When you're speccing out a new product, how do you decide between a legacy LDR and a modern silicon photodiode? It's all about knowing your trade-offs. LDRs are completely unbeatable for cheap, rugged, dusk-to-dawn switching where speed just doesn't matter. But if you're building a barcode scanner or an optical data receiver, you absolutely need the microsecond precision of a photodiode. No question.
Comparing all three major optical options side by side puts it all into perspective. It really highlights a core engineering philosophy. The LDR is king for simple qualitative light detection, basically answering, hey, is it dark out? But the second you need exact quantitative measurements, you're reaching for the photodiode or phototransistor.
So, knowing all the latency limits, the massive temperature drift, and those pesky RoHS restrictions, is an LDR still going on your next bill of materials, or is it finally time to upgrade to a photodiode? Every component carries technical debt, so I'll leave you with that thought to chew on for your next hardware design. Thanks for joining me on this explainer.